Today we are going to cover section 2.1, graphs of basic functions and relations. Be sure to copy your title and your essential question. What are the important defining characteristics and representations of a function? Go ahead and place your cutout, copy example number 1, and we'll start once you're ready. Go ahead and pause it. Excellent. Continuity. This is an informal definition. We're going to continue with continuity once we start chapter 13, which will be the last chapter of the class, as we get you guys ready for calculus. A function is continuous. So we're talking about a continuous function if there's no interruption in the graph of f of the function. The graph of a continuous function has no breaks or holes. So in order for it to be continuous, there's no interruptions. You cannot have any breaks or no holes in it. And this is, as we say, it was an informal definition. A continuous function over an interval of its domain if it's hand-drawn graph over the interval that can be sketched without lifting the pencil from the paper. So we have a continuous function if you're able to just place your pencil and draw it without lifting it, and if there are no gaps in there. So for example number 1, indicate the intervals of the domain over which in which they are continuous. So we need to be able to identify the intervals in which they are continuous. So if you notice on graph A, we have a parabola, and we can start, and we can draw it all the way through without lifting a paper or pencil. There are no gaps, there are no holes, there are no breaks, so therefore this is a continuous function. And one of the things I need to remember is that the interval that we're going to be writing in this section is going to be the interval of the domain. So therefore, we know that this graph starts from way beyond the left. So even as we go over to the left as -5, -6, there's going to be a graph. So therefore, the interval of the domain where it's continuous is going to be from -infinity to +infinity. And just like we covered before, remember that infinity always will give parentheses because we never reach it. We get closer and further away at the same time. Letter B. So in this case, we have a function that is not fully continuous. There's a gap. So we start here, and then there's a small gap in there. Then we start once again from here on. So therefore, we have two intervals that are continuous. One of the things that you have to remember is going to be the interval of the domain. The first one is going to be from -infinity all the way up to 2. At 2 there's a break, so it'll be from -infinity all the way to 2, and from 2 all the way to +infinity. And we can also we can place a union in here as instead of an and. But in this case, there are two separate intervals. Take the time to copy down or paste the cutout and pause it, and we'll start once you're ready. So on a function, we are going to have intervals where a function is increasing, decreasing, or constant. So suppose that a function f is defined over an open interval, I. If f increases on the interval I, whenever, and let's go through this definition. So if it increases, notice that in this case, x1 is less than x2, and you have your x1, x2 right over here. That means that if you plug in a x1 into the function, which gives you this point here, and you plug in a x2 into the same function, this one here, the first value, remember that this is your y value. The first y value will be smaller than the second one. That means that it's going to be increasing in that interval, correct? That should make sense. If the first one's lower than the second one, that means that it's going to be increasing. So that is a formal definition. The function decreases on a specific interval whenever x1 is less than x2, and if you plug in the x1 into the function, whatever the equation is, and you plug in x2 into the function, whatever the equation is, if the first value gives you higher or bigger, larger than the second one, that means that the function has to be decreasing. And it's constant if for every value between x1 and x2, whenever you plug in the value of x1 and x2, if it gives you the same value throughout, that means that it's going to be constant. So if you get the same value throughout, that's going to be constant. So those are more formal definitions that you guys will see once again next year in calculus. So let's go through example number 2. Go ahead and copy it down, paste your graphs or copy them, and then we'll start once you're ready. Go ahead and pause it. Determine the intervals over which the function is increasing, decreasing, or constant. So therefore, if we start from here all the way over here on the first part of the graph, and you notice that we have 3 sections in the first graph. From here to here, is it increasing or decreasing or constant? It's increasing, correct. So therefore, from negative infinity all the way up to where? One of the things that you have to remember is that we are going to write down the interval of the domain. So it's from negative infinity all the way up to 2, negative 2. And even though it's closed, the intervals will always get parentheses. So whenever we talk about interval, it will always get a parenthesis. And in this case, this is increasing. On the second part, which is this section here, that's going to be decreasing. So we from negative 2 all the way to 0. And remember that whenever we're working with intervals, for increasing, decreasing is going to be always parentheses, because therefore we're in this at this specific point is neither increase or decreasing, and you'll find more of that in calculus and as we go into the last chapter of this class. So that'll be decreasing. And that is this section here. And for the last one, that'll be from 0 all the way to positive infinity. Is going to be increasing once again. So try letter B and C, see what you get, and then we'll check your answers once we're done. Go and pause it. So on letter B, we start here and it continues to increase throughout. So even here, it's continued to increase, even at 0, 0. So therefore, we only have one interval. Your interval is from negative infinity all the way to positive infinity, and that is increasing. For letter C, we have one interval, we have our second interval, and we have our third interval. And just be careful. One of the things that throws people off is in this interval, that is the first one from negative infinity all the way up to negative 2 once again. Is that increasing or decreasing? Even though the arrows, um, even though the arrows pointing up, we're reading it from left to right, so therefore it's decreasing. For the second part, it's going to be constant from negative 2 all the way to 3. It's a constant. And for the last one, it's going to be increasing. So if that last interval is from 3 all the way to positive infinity, and that is increasing. Parent function. So one of the things that your calculus teacher is going to expect from you is to be able to have an idea of what the graph looks like. So we have a linear, quadratic, cubic, absolute value, square root, and reciprocal. And you actually have the equations right below. See if you can sketch each of the graphs. So for example, linear, y equal to x. Do you know what that graph looks like? So either by name or by the equation. So linear equation, and so just make a quick sketch. I'll let you guys do each one. Try and see how many of them you know. So you have 6. Go and pause it and make a sketch. Make sure that you do it in pencil so we can go back and correct them. You got it? So in this case, a linear function, we know a linear function has to be a line. And what we call a parent function means the most basic graph. And one of the things that you have to remember is that if you don't know the equation of the graph, you can always just plug in points. So if I plug in a 1 for the x, you get 1 for the y. Plug in a 0, gives you 0. If you plug in a 2, gives you 2. Plug in a 3, gives you 3. And we have our parent graph for linear function is just our diagonal. Make sure that you guys are using ruler. Quadratic. A quadratic will be a parabola. But the parent function is just the most basic function, which is x squared. So if plugging in 0 gives you 0. If I plug in a 1, 1 squared is 1, and I'm going to reflect it. Plug in a 2 gives you 4. Plug in a 2 gives you 2, 4, and I'm going to reflect it. So therefore, that is the parent graph. Cubic. X to the third looks something like this. 1, 2, 3. So if I plug in a 0, gives me 0. I plug in a 1, 1 to the third power is 1. Plug in a 2, 2 to the third power is 8. 2, 4, 6, 7, 8. Plug in a negative 1 gives me negative 1. Plugging in -2 gives you -8. So way over. So therefore your graph comes up and goes back up. That is a cubic. Absolute value. So this is an absolute value of a line. So therefore you just have to think that all these negative values will become positives. So if I plug in a 0, it gives you 0, plug in a 1 gives you 1, plug in a 2 gives you 2, plug in a 3 gives you 3. Plug in a -1 gives you +1, plug in a -2, absolute value of -2 is +2, and so on. So therefore this is the parent graph of an absolute value. Square root. Do you remember what square root looks like? Right, it looks something like this. So plug in a 0 gives you 0. Plug in a 1 gives you 1. Plug in a 2, what's the square root of 2? We have a 1.3. Plug in a 3, which is the next perfect square that I can plug in. Plug in a 4 gives you 2. So therefore it looks something like this. If I plug in a negative, I can't plug in a negative number, so there's no graph on the left. Your domain will be from 0 all the way to positive infinity. And how about the reciprocal or the rational expression 1 over x? Correct. It looks something like this. It has two parts, one here and one here. Plug in a 0 will be undefined. Plug in a 1 gives you 1. And if you plug in a -1, gives you -1. So therefore, your graph looks something like this, where we have a horizontal and a vertical asymptote on your x and y axis. So those are the parent graphs that you need to be able to know. And as you move on to calculus, you kind of need to be familiar with all these graphs and additional graphs that we're going to cover. We cover linear, quadratic, cubic, absolute value, square root, and reciprocals. And this one, so you have graph back from algebra 1 and algebra 2. Go ahead and take the time to copy this down. And in this case, I just made graphs that are 3 by 3. 3 to the left, 3 to the right, up 3, down 3. So you're able to fit all 4 on your paper. And then we'll start once you're ready. Go and pause it. So we are going to explore the symmetry with respect to the x-axis, symmetry to respect to the y-axis, and to the origin. So I'm going to select a point. I'm going to select the point 2, 1 is a good point for us to use. So that is 2, 1. Now I'm going to take this point and I'm going to use my overhead. And what I want to do, I'm going to reflect it to respect to the x-axis. So this is your x-axis. So what happens if I reflect it with respect to the x-axis? So if I reflect it, it's going to be right over here. Do you guys agree? So therefore, this was my original, my reflection will be here. So what are the new coordinates of your new point? It's going to be 2, -1. So what changed? Correct. Your 1 became -1. So therefore, your y value was +1, became -1. So your y is going to become the opposite. What if you reflect this point on the y-axis? What's going to change? So if I take this point and I reflect it with respect to the y-axis, then when I reflect it, it's going to become this point. Do you guys agree? It's going to become this point. So therefore, the new location, once I reflect it, is going to be -2 and up 1. Therefore, what changed? Correct. The x value. Now it used to be a +2, now it's a -2. So therefore, when reflected with respect to the y-axis, you're going to change your x, it's going to become -x. And whenever you reflect it to respect to the origin, basically it will be just reflected it twice, and it's going to become this point here, and you're going to be from -2 and -1. So your x is going to become a -x, and your y is going to become a -y. You basically just change both. And that is whenever you reflect it with respect to the origin, it's basically going to be 1, 2. So take your time to copy down your cutout or paste it in example number 1, and we'll start once you're ready. Go and pause it. So we have an algebraic test for symmetry, and then we're going to do a graphical test for symmetry on example number 4. So remember that you need to be able to have a good representation of your algebraic and your graphical. So you need to be able to know what's a reflection on the x-axis. So if you reflect a figure with respect to the x-axis, what is it going to look like? Or how can you find to see if a figure is going to be symmetric with respect to the y-axis? So you need to be able to do two things, algebraically and graphically, and we'll practice both. The graph of an equation is symmetric with respect to the x-axis if replacing, so whenever you're testing to see if it is symmetric with respect to the x-axis, you're going to replace the y with the -y. And it should yield an equivalent equation, and this is essential. We'll come back to this in a second. A graph of an equation is symmetric with respect to the y-axis. That means that we're going to replace x with -x. It's going to yield an equivalent equation. And if it's symmetric with respect to the origin, that means that we're going to replace the x with a -x and the y with a -y. It's going to yield an equivalent equation. So let's try example 3. Use algebraic test to check for symmetry with respect to both axes and the origin. So therefore, they give us an equation. Do you know what the equation looks like? So we'll go over this later on. So this should be a parabola, correct? So therefore, I need to be able to test for symmetry with respect to the x-axis, with respect to the y-axis, and with respect to the origin. Now, to check for symmetry with respect to the x-axis, I'm going to replace the y with the -y. So therefore, I'm going to write down this equation, but instead of the y, I'm going to replace it with -y. Now, it is essential that when you do a substitution, you place them in parentheses. And I know there's always a few kids that start getting messy with their work. And I need to see the substitution. You can't just say, well, I'm going to plug in a -y, so I can say positive. I need to see the first step as well. And now I can simplify. So I have x minus negative y to the second power becomes y squared, and therefore I don't need parentheses any longer. You can still do it, but I'm just going to skip that one step. And now I need to be able to decide, is this equivalent to the original? Does it yield an equivalent equation? Yes. So therefore, it is symmetric with respect to the x-axis. To check to see if it's symmetric with respect to the y-axis, I'm going to replace the x with a negative x. So therefore, I'll place in parentheses minus y squared equal to 1. But instead of the x, I'm going to replace it with a negative x. And I'm going to simplify. It's not being squared, so not multiplied by anything, so just negative x minus y squared is equal to 1. And I need to ask myself, does it yield an equivalent equation? No. And you may want to be able to place an arrow so that way you remember. And with respect to the origin, I'm going to replace the x with a negative x and the y with a negative y. Now I'm going to simplify negative x minus, this becomes positive. And does it yield an equivalent equation? It does not. So therefore, this equation is only symmetric with respect to the x-axis. Remember to show me the final sentence. Make sure that you show me the work for each one. And I do need to be able to see the substitution as you go through the work. Letter B. Try it, pause it, see what you get, and then we can compare our answers. Go and pause it. Excellent. So in this case, we need to check to see if it's symmetric with respect to the x-axis, y-axis, or the origin. To check to see if it's symmetric with respect to the x-axis, I'm going to replace the y with a negative y. So therefore, I have negative y equals x to the fourth minus x plus 1. And now I'm going to simplify, so I just have negative y equals x to the fourth minus x plus 1. Now, one of the things I have to be careful is that I wanted to see if it's equivalent to the original equation. So therefore, this y equals, I want to be able to take one extra step and either divide by negative 1 or multiply both sides by negative 1. So I'm going to multiply this by negative 1, becomes a positive y, because I want it to be y equals. That becomes a negative x to the fourth, becomes a positive x, and that becomes a negative 1. Does it yield an equivalent equation? No. With respect to the y-axis, I'm going to replace the x with a negative x. So you have to memorize this for the test. Negative x. Negative x to the fourth power, because it's even power, is going to stay positive x to the fourth. Negative is a positive x and plus 1. Does it yield an equivalent equation? Almost, except for the x. So therefore, this is a no. And with respect to the origin, we're going to replace the y with a negative y, the x with a negative x. the x with the negative x and plus 1. So negative y, negative x, negative x. That stays as negative 1. Negative x to the fourth power is an even power, so stays as positive x to the fourth. Negative and negative becomes a positive plus 1. I want still to have y equals, so I need to go through an extra step and multiply by negative 1. Becomes y equals negative x to the fourth minus x minus 1. And that's a yield and equivalent, and that's a no. So this graph is not symmetric at all. So not symmetric. So remember that I do need to be able to see your substitution as you go through this process. That will take us to even and odd function. That this is going to repeat, and we're going to be talking about this throughout the year. So take some time to copy it down, paste it, example number 4. Go and pause it, and we'll start once you're ready. So even and odd functions. A function is said to be even if its graph is symmetric with respect to the y-axis. It's even if it's symmetric to respect to the y-axis, and it's odd if its graph is symmetric with respect to the origin. So let's go into decimals. I'm going to go into decimals, and I'm just going to start my graphing calculator. And if I want to be able to type in a graph that is, actually let me just go into a different. We're almost there. And you can use, I'll place a code on this YouTube so you can actually do this as well. First, you can go to the first screen and just match them. Try to do it by memory without referencing it. So you can match and say, okay, which is y to the x. So each one should have a map. So let's see, y squared, I'll start you guys with the first one. There you go. And then continue on. Then on this screen, see if you can type in what's an equation that you know that's symmetric with respect to the y-axis. That means that it's going to be symmetric on the y-axis. So it'll be one equation. Do you know? So for example, if you have y equals x, that one's symmetric to the origin. If I do x to the second power, that one's symmetric to the y-axis. I need one that's symmetric to the x-axis. We can just place the square. So that will be a graph that's symmetric to with respect to the x-axis. One that's symmetric with respect to the y-axis will be one of the graphs. Y equals, correct, x squared. What's another one? Y equals absolute value of x, or you can also do the bars. Either one works. Or you can do ABS and then parenthesis x. So those are symmetric with respect to the y-axis. How about a graph that's symmetric with respect to the origin? Well, we cover one of them, right? What's another one? X, y equals x to the power of 3. That is correct. And now we're going to cover even and odd functions. So this is the terminology that you also need to be able to remember. A function is even for if for each x in the domain of f, when you plug it in, you're going to get the original function. And we'll go over this notation in a second. Remember, if it's even, it's going to be symmetric with respect to the y-axis. If it's odd, it's going to be symmetric with respect to the origin. So therefore, if it's odd, for each x in the domain of f, when you plug in a negative x, you're going to end up with the opposite of the function, so the negative of the function. Even if you plug in a negative x, you end up with the original function. You got it? So let's try example number 4. It'll make a little more sense. So determine whether the function f of x equals x to the third minus x is an even function, odd function, or neither. So to be able to now, one way to do this is to substitute this with a y and then go through a process that we did here. But actually, we need to be able to be more comfortable with this notation, the function notation. So what we're going to do, we are going to replace your x with a negative x. So be f of negative x is equal to x to the third power minus x. If I still the x, I'm going to replace it with a negative x. And now I'm going to just simplify. F of negative x is equal to negative x to the third power will be negative x to the third. Remember that you are multiplying your negative x 3 times. So that's 1, 2, 3. And that gives me negative times a negative is a positive x squared times a negative x. That gives me a negative x to the third. So therefore, when you know at this point that you have a odd exponent, you're going to end up with a negative. Negative times negative gives you a positive x. So therefore, I need to check, is this, did I end up with the original function? No. So therefore, I know that this is not even, not an even function. Because if it was even, at this point, this will be exactly the same as the original function, just like it states here. So now what we're going to do, we're going to see if it's odd, we're going to factor a negative 1, or just a negative. So f of negative x equals, I'm going to factor a negative, and then we have x to the third minus x. Do you agree? Did I end up, is this the same as your original function? It is. So therefore, f of negative x is equal to negative. This is your f function, and therefore that is the notation that we use. The function is odd, which means that it's symmetric to the origin. Example number 5. We'll copy it down, and then we'll try it. See if it's symmetric to the x. See if it's even or odd function, or neither. Go and pause it. Copy it down. Try it yourself, and then we can compare our answers. Excellent. So to determine to see if it's even, odd, or neither, what I'm going to do, I'm going to replace my x with a negative x. 8 x to the fourth minus 3 x squared. And now I'm just going to simplify it. I have f of negative x equals negative x to the fourth power. Because it's an even, it becomes a positive. So it gives me 8x to the fourth. Negative x to the second power, it's an even exponent, so it makes it into a positive. So I have a negative 3x squared. And then I need to check and see, is this the same as my original function? And it is. So I just need to go to the extra step. So f of negative x, and I'm going to replace this is equivalent to my original function, f of x. So therefore the function is even. And once again, on your homework, I'll be looking for the following. I'll be looking for your substitution, your correct simplification, and the final notation. Last example for today. Oh, we have two more. So now we need to be able to know the algebraic aspect of it. The graphical. We did the algebraic, now the graphical representation. Remember, you need to be able to connect algebraic and graphical. What does it mean to be an even or odd function? So determine whether the function, and this is the equation, we're going to be, yes, last year you guys graphed sine and cosine, tangent, cotangent, cosecant. So you should be familiar with the graphs, and we'll be doing this once again this year in one of the future chapters. So I need to determine if it's even or odd. So you should be able to know by the graph. So I know that if it's even, it's symmetric respect to the y-axis. So in this case, notice that it's not symmetric to respect to the y-axis. So I know that it's not even. The question is odd. It's odd if we get this one here, we end up with this is 1 in 4, and this point is negative 1 in 4. So therefore this is a odd function. Now that we know it's an odd function, we need to find f of 3. So find f of 3, f of negative 3, f of 1, f of negative 1. Go and pause it, see what you get, and then we can continue. So what's f of 3? F of 3, 1, 2, 3. You plug in 3, you end up with negative 4. F of negative 3, positive 4. So that's what an odd function is. If you plug in a 3, you get negative 4. But if you plug in a negative 3, you get the opposite. Plug in a 1. Plug in a 1 gives you 4. Plug in a negative 1 gives you negative 4. That is what an odd function does. If you plug in the opposite, it gives you the opposite as well. And the last example for today. Go and copy it down, and we'll start once you're ready. Go and try it. See if it's an even function, an odd function, and find a pattern. Excellent. So in this case, this is a even function. If I plug in a 3, I end up with 2.5. If I plug in a negative 3, I end up with 2.5 as well. So that's what an odd function does. If you plug in a 3, you end up with 2.5. Plug in a negative 3, you end up with the same value. Where in odd function, it gives you the opposite value. F of 4, plug in a 4, gives you a 2. Plug in a negative 4, gives you also a 2. So this type of questions will be on your test as well. So go and Do me a favor, write down a summary, and I'll see you guys next time.